Welcome, calculus friends. This is going to be a video where you learn about something called the integral test, and it is a test for series convergence. This entire unit is really going to be about looking at series and seeing if they converge or diverge. And every lesson, you will learn one or more new ways of assessing that. For this video, it would be helpful to have your infinite series roadmap available, as well as the ability to take notes. So if you look at that roadmap, I would like to focus in on some of the things up at the top. So where it says enter here, when you're asking yourself if the limit of the terms goes to 0, just thinking of it as a sequence, that is what we would call the nth term test. Okay, so if I don't have terms that are going to 0, I automatically know I have a divergent series. Next to that is a check to see if the terms are getting smaller as we go on or not. So if the terms are not getting smaller, in other words, if they are getting bigger, think about this analogy. So this analogy is one I got from Mr. Aronson, my good friend, when I started teaching BC. Predates Mr. Covey's involvement here. And Mr. Aronson said, think about being on a beach, which I enjoy thinking about. And he said, imagine that you have buckets of sand that you are dumping into a pile. So if the buckets are getting larger and larger and larger as you dump more and more and more sand into the pile, then that pile is just going to continue to grow. Okay, and so certainly you know that if the terms are getting larger, then you have something that is going to be a divergent series. Okay, now that said, tricky thing. So if that limit is going to 0, if the terms are getting smaller, does that automatically guarantee convergence? Well, hopefully you learned last fall that that is a tricky statement and we have to be careful. This is what the nth term test is actually all about. So if I have a convergent series, then that does mean that the limit of the terms as a sequence is going to 0. Now let's look at this if-then statement, okay? An if-then statement is not automatically reversible, right? So if A then B does not imply if B then A. The contrapositive is the one that would be logically equivalent. So I take this conclusion and I negate it. So if not the limit going to 0, then not series convergence. Okay, now that's a really awkward way of writing that. So we would normally write this without the English in it so much and use more math. So if the limit of the terms as we go toward infinity is not 0, then the series of those terms, and usually we have an n here, that's a little bit sloppy on my part there, then the corresponding series diverges. That, my friends, is the nth term test. Okay, so just be cautious about what it tells you and what it does not tell you. Now, all of that said, I just wanted to remind you that we do want to think about this easy way of throwing out some problems, right? Because the nth term test is easier. And we also want to consider these easier ways, geometric, telescoping. Those are easier methodologies than the things we're going to learn later in this unit, by and large. Okay, you might find ones that you really like personally, but generally speaking, those are your easier outs, if possible. Okay, now we're going to kick off looking at the integral test by considering two situations that seem rather alike, but actually are quite different structurally. Okay, so I'm going to follow my own advice and consider the nth term test. This is the series I want to look at. And so I'm going to think about that limit as we go towards infinity of the sequence of terms. I'm just literally thinking of plugging in 1, plugging in 2, plugging in 3. So this is the sequence I'm thinking about, going on forever. And that limit would be 0. Now remember, when you get the result of 0, you know 0. Okay, so that doesn't tell me anything. No information really from that. Okay, are the terms decreasing? Well, we can observe, since I wrote out a few terms, it sure does look like they're going to be getting smaller for all time. And so I'm going to say here, yes, just from logic, but we also could show this because we are calculus students. So if we were to consider the related function, I'm just writing this in a continuous manner just to make it kind of make more sense to our heads. The first derivative there would be -1 over x squared. And regardless of the value of x, with the exception of 0, that is always going to give us something negative, and negative rates of change mean decreasing. So we can even show that with a derivative. Now, we know from kind of mentioning this maybe in class, at least I'm recording this video before having class, so I intend to mention this in class, but we did look at this as an example. This is the harmonic series. And we have an idea that this diverges from that discussion, but what we really need to think about is this. We need to have some sort of methodology to see if this gets small enough, fast enough, that it's going to be the situation where the buckets of sand, add up to something finite rather than going to infinity as a sum. So it's great that it's getting smaller term by term, right? That's what this limit is, getting smaller, decreasing, right? That's great, but we don't know if it's getting small enough, fast enough yet, okay? So leave a little space there in your notes, okay, if you're taking your own notes, and we're going to take a look at a similar problem that, like I said, is going to be structurally different. Okay, so again, same procedure. Start at the top of the flowchart and check your nth term test by thinking about the terms of this sequence as n goes to infinity. Now, those terms certainly are getting smaller, 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 approaching 0, but that means that we don't know anything. Okay, you know 0 when you get 0. Okay, then are the terms decreasing? Well, yes, we could show this with a derivative even. I won't really take the time to do that because I already mentioned the idea. But that derivative is going to be less than 0 for everything other than 0 itself. So yes. And again, we need something about getting small enough, fast enough, or not, okay, whichever way. So let's think about this graphically a little bit, okay? So what I have over here is a picture of the related function y equals 1 over x cubed. And you might think, okay, so if I'm adding up, which is what this summation sign means, what is it that I am adding up? Well, I'm adding up the terms of that series. And so it's like this sum. Well, if I think about this graphically, I could make a connection and say, well, this is also just like taking rectangles that are 1 unit wide and then finding the heights of rectangles on this function. Because if this is at, x equals 0 here, and this is at x equals 1, then this line would represent the function value at 1, and this would be the function value at 2, and this would be the function value at 3. And those are exactly the terms of this series. So if I were to find the area of the different rectangles and add them up, that would be equivalent to adding up the terms of this series. Whoa, adding up rectangles. Have we ever done that before? Kind of like all the time, right? So adding up rectangles and then letting the width of the rectangle become infinitesimally thin so we have infinitely many rectangles to fill up, that sounds awfully like an integral. Okay, so here is my totally stolen from the interwebs picture of the integral test. Okay, so it is the case that the series and the integral have the same behavior. So either the series and, oh, I did not mean to do that. Either the series and the integral both converge or they both diverge. It's important to note that they have the same behavior. The value is not necessarily the same. Okay, so this is a test where you test the integral that is related to the series, and you know that the series itself will behave the same way. Okay. All right, so I think that's all I need to say about that slide. All right, and this is the actual statement of the integral test. So we've had a few cases lately where Mr. Covey and I have tried to emphasize to you how College Board can be a little fussy, shall we say, about how you're going to go about checking or about applying different tests. Okay, and this is one of those. When you use the integral test, they do want you to mention how you have a function that's continuous, positive, and decreasing. Those are the three things that they want you to explicitly call out. And then you can look at the integral that's similar to the series in order to assess what is going on with the series itself. Okay, now we're going to go back to the two questions that we had above. If you're looking at my notes page, but back in your notes regardless. And we're going to look back at these two series and actually do the integral test. Okay, so trying to use an integral test here, I need to at least double check in my own mind that I have the three conditions that I would write about on my AP exam. So I need to check for continuity. I need to check that the terms are positive, and I need to check for decreasing. Well, decreasing we checked up above already, okay? Positive means that the terms actually aren't negative. Sorry, that was going to be a wiser statement than that. But 1 over x is a function that looks like this. And you might say, well, wait, we have a problem because look down here. And I would say, no, we don't, because in terms of series, your domain is you plug in a 1, you plug in a 2, you plug in a 3. So all of these terms live in positive land, so we're okay there. And continuous, again, we have an issue at 0, but that's not problematic for the domain that we're thinking about when we think about series. So we're okay on that, okay? It also occurred to me just as I was talking about this that I did not mention back here that your integral test can have a lower bound of basically a lot of different things. You can start further down in the series than just 1, okay? So the idea there, I believe, if I understand this correctly, which I think I do, is if you start from, say, like 5, and from 5 to infinity is finite, and then you added together a few more terms beyond that, it would still be finite. Whereas if you go from 5 to infinity and that results in something that is divergent or infinite, adding a few more terms to that is not going to change that result. So your lower bound can shift a little bit in order to accommodate these three conditions. Okay, so just bear that in mind. Okay, there's a question later on where that comes into play. It is not this one. Okay, so we would write out that we're doing the integral test. Always, always try to identify which test you are doing. It is, a lot of these tests can look similar, not so much the integral test, but a lot of the other tests can look sort of similar. So it helps the reader to be able to follow your work if you label it. Okay, and I've checked my conditions. I'm saying I'm doing the integral test, and then I'm going to write my improper integral that's related to this question. Okay, and so we are looking at the harmonic series. So this is the related continuous function, continuous, excluding 0. But we're fine because I'm saying I'm starting from 1, like over here, and I'm going to infinity. So I'm looking at this region. And I want to know if that region has a finite area or an infinite area. So this plays into what we learned in our previous unit. We're just going to anti-differentiate, et cetera, et cetera. So I know that my antiderivative is natural log absolute x. Here are my bounds. If you wanted to write that with a b instead, out of habit, that would be totally fine. I do kind of shift to an n when I'm doing integral test usually. Habits. Okay, and then plug in your bounds. Fundamental theorem. And then think about your limit. Well, natural log of 1 is 0, so that is just 0. And then as I let this argument get bigger and bigger, what happens to the natural log function? Well, natural log itself looks like this, right? Just natural log of x, right? Y equals natural log of x. So as I'm going bigger, bigger, bigger this way, this is getting bigger, bigger, bigger. Absolute value does not change that tendency. So this is a limit that goes to infinity. So I would say that my sum diverges by the integral test. Now this is another good place right here at the end to mention the name. So like if you don't mention the name at the start, throw it on at the end just as an identifier, and I think that that's a really helpful thing to do. Okay? All right, so we know that the harmonic series diverges. All right, let's go back to this one. This was similar but different. I already told you it's different, so hopefully you know that means it converges. But let's do our integral test. We need to check our conditions. So we should check, is our function continuous? The only discontinuity is at 0, and we can avoid that by how we set up our integral. Are the terms positive? Well, 1 over x to the third does have the ability to yield a negative result, but not for the domain that we're talking about. We're talking about series, so 1, 2, 3, 4, 5. So we're good on this, we're good on this. And the decreasing part, if I were to go and think about this derivative, that would be that guy, and that's always going to be negative because x to the fourth in the denominator is always positive, so we've got that. Now note, I don't think you need to especially do a lot of like written work for those checks. However, name them on your paper and show that you've thought, basically show that you've thought about them, that you know what the conditions are and you have considered them and have them. Now, understand, in my experience grading papers, sometimes I'll have students who write out these conditions and they don't actually do the thinking, they just draw a check mark. And then if one of those conditions isn't met, you're busted, right? So make sure that you actually do the thinking that this writing is supposed to indicate. All right, so then we write out our improper integral. It's 1 over x to the third, so I'm going to write it like so to make it more calculus friendly. This time I will use a b, what the heck. Okay, and starting from 1 works just fine with this. So we're going to go ahead and do our antiderivative. Have our bounds over here. Then use fundamental theorem. Plug in my bounds. I'm going to make that more algebra friendly now. Because that will be easier for me to think about when I'm thinking about this limit. And that's the last thing that I have is thinking about the limit. So I have over here the value of a half. This is getting bigger, bigger, bigger right here, which means that this whole thing is getting smaller, 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 going to 0. So I get a half. So that means that my corresponding series is convergent. Therefore, this series converges by the integral test. Now, I do not know that this series adds up to a half. I don't know that, okay? Perhaps, perhaps not, but that is not the point. Finding the value of the series is something that was nice when we had telescoping series. It was nice and it was possible when we had geometric series. Generally speaking, though, in the broader picture of things, you are not looking at series convergence to find out what their sum is. You are just trying to categorize things. Are you convergent or are you divergent? That is the task, okay? Now there's a huge slew of problems at the end of this note set, okay? And so I'm going to ask that you try these problems and then come back and I will show and possibly have some highlights on some of these, but I don't want this video to get exceedingly long. And then after we go through those little examples, I'm going to talk with you a little bit more about something called p-series. On this screen right now, you can see where the integral test is located in your flow chart. So if you are interested, something that my former students have done is as we learn different tests, they have added labels or they've highlighted around things so that they can see which ones they've learned or use some color coding. So that's something that you could choose to do if you think that would help the flow chart be more useful to you. All right, so, oh, this was supposed to be my space to do those. I guess I didn't pay attention to my own setup here very well. Okay, so these questions, it's problems 1 through 5 in the prepared handout. I would just like you to try setting up the integral test with each one. And in question number 4, there is something of interest in terms of what bounds you pick. So if you're not quite sure about that, you could leave number 4 aside. But if you do figure it out, that's awesome. I would invite you to pause the video and try problems 1 through 5. And when you come back, we will take a look at solutions. Okay, welcome back. Thank you for trying those 5 questions on your own. That is the way that you're going to learn, is by testing out your own understanding. So in question 1, you see here that I have writing over here. This is the kind of thing that you just kind of write off to the side to make sure that you're checking that you have continuity, positive function, decreasing. Okay, just like a mental check, making sure that you actually can use the test. If any of those conditions doesn't hold, you can't use this test. You have to use a different test, okay? When you're going to have a lot of tests, right? I mentioned to you that we learn like 1 or more a day. So you don't have maybe a lot of choices yet, but you will. So this work shows setting up your integral. Feel free to pause it as necessary, but you should have gotten a limit that does not have a finite value, which means therefore your series is divergent, okay? I would like to show an example of written out work back here. Notice that if you actually do a u substitution, you should remember to change your bounds to be in terms of u. It might be easier at this point not to have to show that, right? So maybe do a side problem with an indefinite integral, just finding the antiderivative if you need to do that kind of writing out, or just remain in the variable of x for clarity. You do not want to write something that is not mathematically true. So I know from my experience AP grading that if you have an equal sign in between two things, like let's say you'd forgotten to change the bounds and over here you wrote n and over here you wrote 1, even though your integrand is now in terms of 0, writing an equal sign that is false is what's called a linkage error. And there is no way you get away with a linkage error, okay? It is just, you have to be cautious, okay, about that equal sign. Equal sign doesn't mean, and now I'm thinking about this. Equal sign means equivalent. So make sure that you're using it to mean equivalent. All right, the second problem, you know I love this because guess what? We get to see arctan. So over here is the check of conditions, which we do have. And then let's discuss what happens, I hope. Oh my goodness, I'll be so sad if not the case, but hopefully we recognize that this is a straight out of the box arctan. And so here is our limit statement. And then we are looking at the limit as we go towards infinity. Remember what arctangent graphs like, okay? This is like a classic thing. So, oops. Oh, sometimes it just, I don't know if this happens to Cubby, but I think like the pen changing doesn't pick up as fast as I want it to. I shouldn't say I think, I know that is my experience. So arctan has the horizontal asymptotes that correspond to the vertical asymptotes on the tangent function. So arctan looks like this, which means that this asymptote is at pi over 2, and this asymptote is at negative pi over 2. So if we're looking at arctan, as the argument gets bigger, 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 we're asking what happens to this function as we move further and further to the right. And that means we are approaching pi over 2. And if, oh, you really need to know that arctangent of 1, the angle whose tangent is 1, is pi over 4. Okay, that's like a unit circle thing. So this question is just beautiful. I'm just saying, there's a lot of pretty math in that. All right, so that one converges because we got a finite value, the finite value being pi over 4. All right, let's take a quick peek at 3 and at 4. In number 4, notice that this starting value for the index variable was at 2. And so technically, I don't know if they would be actually very fussy about this on the AP test, to be honest, But technically, we shouldn't have a 1 down here, because if we take the natural log of the natural log of 1, well, natural log of 1 is 0, and natural log at 0 is not defined. So this is just really keeping things legal. Could I pick a different number here? Yeah, I could pick 3 or 4 or 5 or 7.9. Those are all possibilities, because that lower bound isn't really the key feature. We're looking for infinite versus finite, okay? And so that little bit of slide isn't going to change that result. Both of these should end up being divergent. I'm just going to pause for a second in case you need to write something down. Okay, and here is our result for question 5. This one is convergent. And something that's of interest in this question, because of where we're headed, is that we could write this with just, n to the something, right? N to the 3 halves, which means it's a series that is n to the negative 3 halves if we rewrite it, okay? So that is an example that kind of matches the first 2 problems that we did in this video to some extent, right? If we go back in time, at the beginning of this video, we looked at 1 over n, which we could think of as if it were n to the negative 1, right? That series. And then the second example we looked at was a series of n to the negative 3. Okay, so those are 3 examples that we've looked at. One of them was divergent. 2 of them were convergent. And this leads into the very last thing I want to talk to you about in this video. Okay, this is probably going to be your favorite series convergence test. It's called the P-series test. So for the 3 problems I just mentioned, those are all examples of P-series. So it's traditional, it's actually kind of universal, I should say, right? It's not just a Lake Forest High School thing, it is a calculus thing, that we think of any series that is 1 over n to a power, P for power, as a P-series, okay? And the turning point between convergence and divergence is that harmonic series. So if I have a p-value or a power that is less than or equal to 1, okay, so 1 is a harmonic series, smaller than that is going to cause divergence. Bigger than that is going to cause convergence. And that, I mean, this test is so sweet because really all you have to say is this is a p-series, p is equal to blank, which puts it either in the convergent category or the divergent category. And so I have a note next to this in the notes packet that just mentions how the p-series is the harmonic series is the turning point in the p-series scope of problems with p equal to 1, okay? On your flow chart, P-series is right over on the left with all of these nice easy things, the geometric, the telescoping, and P-series. Now, to be honest, I inherited this flow chart from a previous BC teacher. I think he did a great job on it. But that said, I actually might even move P-series further up this chain because it is so very, very straightforward, okay? So I just wanted to mention that. The remainder of this set of notes is going to be handled in our class. So thank you for listening and thank you for trying those problems. Bye.